Shalom. Thank you, Moti, Yossi, friends and colleagues. It's a real honor to be here and have the chance to address the Israeli Surgical Association. The topic for today is pancreas cancer and whether we should look at this as a single disease or perhaps as many diseases. The only disclosure I have to make is that my wife, who's a physician, works for a pharmaceutical company that has no impact on what I'm going to talk about today. Now, when we talk about cancer, the big picture, we talk about different tissue origins: carcinoma, sarcoma, melanoma. And when we begin to focus a little more, we say, well, there's not just carcinoma. There are carcinomas that arise in many different organs. And as shown here, these different types of carcinoma have different treatments. Some require surgery, some require chemotherapy, some are highly curable, some are nearly always lethal. Unfortunately, pancreas cancer, which is my specialty, is one of the ones at the bottom here in the 5-year survival. And at the end, we'll talk a little bit about some of our efforts to try to begin to move the bar on pancreas cancer. Now, in the time of my scientific career, we've learned a great deal about cancer biology. When I was a medical student and entered the MD PhD program, we for the young surgeons in the audience, it may be hard to believe this, we had no idea what caused cancer. We knew that cancer somehow was involved genes because we knew there were inherited syndromes. We knew that there were agents that could damage DNA that would cause cancer, X-rays and chemicals, but we had no idea what specific genetic events drove cancer. And it was the discovery that there were genes that could seemingly alter growth properties in a sort of dominant positive way, which we call oncogenes, or genes whose loss released the brakes on cell division, which we call tumor suppressor genes, which seem to play critical roles in cancer. Now, it was in animal models. In fact, you could just take a couple of these genetic events and you could drive a mouse cell to become cancer. Mice, of course, have a short life and short telomeres, and human cells are more complex. But we now understand, as shown on the left side of the diagram, that cancer occurs as the result of probably on the order of 6 to 10 specific mutations in genes that drive specific biological processes. And it's this accumulation of events in a clonal population of cells which is responsible for the disease we call cancer. Now, when we drill down even farther and ask what do these different things do, you can see that some of these play a role in resisting cell death, in sustaining proliferation or inducing blood vessel growth. We also know in some more recent studies that there are genes involved in inflammation, in blocking the host immunity, in the stability of the genome. And again, all of these accumulate to cause cancer. So now we've learned a great deal about a lot of genes. There are 20,000 or 30,000 genes in the human genome. We now know that probably hundreds of them play some role in cancer. So how do we put it all together? And as shown in this slide, the way we do this is with the science we now call genomics, which is to try to take all this data and to look at simultaneously thousands of genes and dozens or hundreds of patients and begin to ask, how does this relate to the process of cancer? And it's also worth noting, as shown in the bottom left panel on this slide, that the cost of DNA sequencing has plummeted over the last 10 years. The first genome cost $1 billion to sequence, the first human complete genome. It's now possible to sequence a genome for somewhere between $100 and $700, and that price is going down all the time. As shown in this slide, it really plummeted. And in fact, towards the end of my talk, I'm going to describe some studies we did at a time that we initiated them. We thought it would cost $10,000 per genome. By the time we were finishing, it was costing less than $1,000 per genome. So just like the amount of memory that could go on a chip, the cost of sequencing DNA has dramatically improved really in a matter of a few years. And as a result, DNA sequencing has become almost standard in a variety of places, including my new institution, where we routinely sequence patients' genomes. There are a lot of issues with doing genetic sequencing, which I won't talk about here, in terms of the way the information is managed, the potential impacts on patients' ability to get life insurance and other issues. So it's not a trivial thing to do sequencing. But ultimately, I think for cancer patients, it's going to be the way in which we define their disease, because it will impact both prognosis and treatment. And that's what I'm going to talk about here. So we can get all this information. We can now get it fairly cheaply. It doesn't cost much more than a CAT scan. How is it useful? And I think breast cancer really has been a wonderful model for where understanding that there are different types of cancer arising in the same tissue can impact both prognosis and treatment. Again, when I was in my early training, we talked about breast cancer in terms of its histopathology. We talked about it as lobular or ductal. We talked about it as in situ or invasive. There were these rare types like inflammatory breast cancer. And we knew that there were estrogen and progesterone receptors, and that probably played a role in whether you should use hormonal manipulation in treatment. But again, it was early days, and it was really unclear what the significance of any of this was. And then came the ability to develop these genomic understandings of the genes present in breast cancer. And these are just a couple of the very early papers that looked at gene expression patterns in breast cancer and began to break them down not just by particular receptors, but by the entire genomic profile. And when this was done, it could be shown that there were groups of tumors that looked quite similar in terms of their genomics, and there were groups of tumors that looked very different. Sometimes this correlated well with our prior understanding in terms of things like hormone receptors or the presence of the HER2/neu oncogene. And what's shown here is that you can break down breast cancers really into four major groups: the luminal A and B, the ERB2 or HER2/neu positive, and the basal subtypes, and that this had a major impact on survival. And what's shown here in the Kaplan-Meier curve down below is that patients who were luminal type A did very well, patients who were type B did less well, and patients who were ERB2 or HER2/neu positive, or who had triple negative breast cancer, that is, they had no hormone receptors and they did not have any abnormality involving the HER2/neu gene, no overexpression. Those triple negative patients did the worst of all. And this just shows that the majority of patients were in the luminal group, but about 20% were in the HER2/neu positive, and about 15% were in the triple negative group. And again, this shows just a different study, but similar results, that the HER2/neu positive and the triple negative had a much worse prognosis. And so when one thinks about informing our patients of their disease, how we plan their treatment, what we should do for them, this is very important. Even more importantly, we began to realize that some types of tumors would benefit from chemotherapy, others did not. So for example, the luminal A, which has the best prognosis, really doesn't respond to chemotherapy very well, but it often responds beautifully to estrogen therapy. So we knew to treat those patients with hormone therapy. Luminal B has a sort of more aggressive biology, often gets both estrogen receptor therapy and chemotherapy, even though the chemotherapy may not add as much. The HER2 positive gets HER2-directed therapy along with chemotherapy. And the triple negative subgroup is an area of very active investigation because we know they tend not to respond well to traditional chemotherapy, but we also are learning more and more about the biology. And now we can focus drug trials looking at specific agents that target triple negative breast cancer. And there are agents now being approved specifically for this subtype. And this just shows the impact of HER2-directed therapy. Again, by identifying this subset, HER2-directed therapy now makes HER2-positive breast cancer the best form of breast cancer in terms of outcome, whereas it used to be sort of the worst, or at least tied for the worst, with triple negative. So it's very clear that for breast cancer, identifying different subtypes of breast cancer has made a major impact on prognosis and treatment. And for those of us who do clinical research, it helps drive and focus clinical research efforts so that we study similar types of tumors and not all types of tumors. An example of the importance of this, HER2-targeted therapies don't work on HER2-negative tumors. If one simply looks at all breast cancer, HER2-focused therapies would never have been approved because a fraction of HER2-positive disease responds. If only a fraction of 20% responds, that total response in the population will be very low. And it's only by focusing on HER2-positive patients that we were able to recognize that these therapies could impact outcomes. So what about pancreas cancer? Pancreas cancer is now the third most common cause of cancer death in the US. The prevalence increased a great deal in the 20th century, but it continues to go up in the 21st. And it's important to recognize this is a disease of an aging population, and I think most Western countries, and I suspect Israel as well as the US, have an increase in the number of older patients who are surviving heart disease, surviving other problems. And as they survive longer, every decade of life, at least into the 90s, the risk of pancreas cancer doubles. So pancreas cancer is already the third most common cause of cancer death. And in fact, it's predicted that by 2020 in the US, it'll become the second most common cause of cancer death, only surpassed by lung cancer. I don't have to tell a room full of surgeons that pancreas cancer is a very bad type of cancer. And part of the reason is that when we diagnose pancreas cancer, it's most often metastatic, stage 4. A substantial amount of the time, it's stage 3, that is locally advanced and still unresectable. But even of those we take to the operating room, a significant fraction are found to be inoperable at surgery. And of those we successfully resect and feel that we've actually potentially cured the patient, the majority will recur. So our ability to impact this disease surgically is limited, both by stage of diagnosis and the fact that the biology of the disease often exceeds our ability to eradicate it surgically. Chemotherapy and radiation are a very modest benefit, and the median survival for patients who are not surgical candidates is less than 12 months. The little graph at the bottom there shows the progress in overall cancer survival between the 1970s and 2010 to 12, I think is the period up on top. What you can see is for many types of cancer, the results are markedly improved. Unfortunately, for pancreas cancer, that bar has shifted almost not at all. And that's where I think understanding the biology and beginning to define the genomics of pancreas cancer is so promising. Now, again, when I talk about pancreas cancer, I'm talking about adenocarcinoma of the pancreas, and this is just a slide to remind us that endocrine cancer of the pancreas is a very indolent disease in many cases, and that endocrine pancreas cancer survival is markedly better than exocrine pancreas cancer, but I'm going to be focusing now on pancreas adenocarcinoma. We know that pancreas cancer is a remarkably uniform disease for a series of common mutations. And this is different than colon cancer, breast cancer, almost any other cancer. KRAS mutations occur in 90% of pancreas cancers. This is a gene that drives cell proliferation. Loss of a gene called CDKN2 occurs in about 90 or 95% of patients. This is a gene that actually controls cell death, particularly in the setting of KRAS activation. So the two going hand in hand makes sense. The p53 gene is lost in many cancers, including pancreas cancer. And an interesting gene, SMAD4, which plays a role in TGF-beta signaling, is lost in about half of cancers and appears to actually create a situation where the cells become much more likely to metastasize. That is, SMAD4 mutant pancreas cancers are much more likely to be widely disseminated. Now, about 5 or 6 years ago, the first studies started coming out looking at whether there were subtypes of pancreas cancer. And this was a paper that looked at gene expression. So it's not looking at DNA, it's really looking at RNA and asking what genes are actively expressed in the cancer cells. And you can see in this paper that there were 3 forms of pancreas cancer defined. There was an exocrine-like form, a classical form, and the quasi-mesenchymal form. And the quasi-mesenchymal form, as you see in the Kaplan-Meier curve on the right, has a markedly inferior survival. So when we look at these different forms of cancer, you can see that some pancreas cancers, based on their gene expression profile, can be predicted to be more aggressive or less aggressive. They're all pretty bad. I mean, those curves all go down to a long-term survival of less than 20%. But the rate of the death is markedly different in the different subtypes. Now, a very extensive study that looked at DNA sequence, not gene expression, but DNA mutations, actually came up with 4 different subtypes. And I won't go into the analysis that led to this. These are sort of not completely overlapping with the 3 subtypes defined by gene expression. But what was important is that both studies began to make some predictions about treatment. In the gene expression study, it was shown that when they looked at cell lines, and that's the bar graph you can see on the left, there were really only two of the 3 subsets, the classical and the quasi-mesenchymal, that virtually all established cell lines represented. And when one looked at the responsiveness of those cell lines to the 2 drugs that were commonly used for pancreas cancer, which were gemcitabine and Erbitux, an EGF receptor inhibitor, you can see that the responsiveness of the 2 different classes of drugs was markedly different. That is, the quasi-mesenchymal ones were much more likely to respond to gemcitabine, and the other group, the classical group, was more likely to respond to Erbitux. So again, we begin to now define subsets for whom we should target therapy. The sort of blown up balloon over there shows that in the second paper that I described, the paper from using DNA analysis rather than RNA analysis, they actually identified a subset of highly genomically deranged tumors. These included BRCA tumors, but also other tumors that appeared to have very abnormal genomes and problems with DNA repair, and then could show that that subset of tumors responded beautifully to agents that damage DNA, specifically to cisplatinum type drugs. And patients had remarkable responses. Again, a small fraction of patients, but those patients probably should be treated with those types of drugs. And so again, many trials now for BRCA patients are beginning to look at using DNA damaging drugs rather than traditional chemotherapy. Now, one of the challenges, this was a paper that came out just last year. Again, genomic analysis, big series, looking at hundreds of patients. They come up also with 4 subtypes, but they're 4 different subtypes. They don't overlap perfectly. There's a squamous subtype, which doesn't really correlate well with the adenosquamous that we see in histopathology, but it's clearly the bad actor. It's sort of similar to the quasi-mesenchymal in the previous survival curve. That is, these are the patients who have the most aggressive tumors, where all the others, and this is a Kaplan-Meier curve, which is based on resected tumors. So you can see median survivals of only a year for the squamous group versus 2 to 3 years for the other group. So again, we're beginning to break down these subsets. The problem is we so far don't agree on who belongs in which subset. Now I'm going to finish just telling you a little bit about the work that I did on the pancreas cancer dream team. This was a big project. I'm only going to tell you about a little piece of it. But as many people know, the original dream team included Larry Bird and Magic Johnson and Michael Jordan. It was the USA Olympic team in 1980. And Stand Up to Cancer decided to fund these dream teams. And a writer actually came to one of our leadership meetings and wrote this article on how to cure cancer. And it says in there, it's possible thanks to the new cancer dream teams that are delivering better results faster. I don't think we're curing cancer, but hopefully we're moving closer to it. The other great thing about this Time Magazine article was that I was actually the centerfold of the magazine. They came to the OR and it took a picture of me doing a Whipple operation. You can sort of see my hands there reflected in the glasses. And this is as close as I'll ever come to being a centerfold. So it was very useful personally. This was a big award. It was based at Penn, but also involved Hopkins, Sloan Kettering, Princeton, Salk, Translational Genomics. We did a whole bunch of trials, which I'm not going to tell you about, but I'm going to tell you a little bit about this one trial just to finish up. Again, big team science, lots of people at a lot of institutions, but all of them were based on patients I operated on. And this shows There were about 109, I think, we ultimately enrolled in the study. You'll notice, first of all, that the 30-day bar is at 100%. It's always good to have low mortality if you're going to try to do this. And it's important to track your outcomes, because the outcomes are what's going to drive your analysis of the data. And the study was very busy. We did lots of things. We looked at the stroma, the so-called stellate cells. We looked at metabolomics, and I'm not going to talk about that. I am going to talk about the DNA analysis work we did. And again, when we started this project, we thought this was a really brave, audacious goal to sequence 75 or 100 tumors. Now, of course, you can have a smart undergraduate student in the lab for the summer, and they can get a good piece of that done. So the science has changed dramatically. We did very deep sequencing on these tumors. In some cases, we did flow cytometry and isolated nuclei so that we could enrich for cancer versus normal nuclei in the specimens. And we learned a couple of really interesting things. The first thing we learned was that about 40% of pancreas cancers have a targetable mutation using drugs that are either approved or are in testing and appear promising for that specific target. So as an example, in the middle of this curve right here is ERB-B2, HER2-neu. So there are about 3% of pancreas cancers that have an amplified HER2-neu, just like the 20% of breast cancers that have an amplified HER2-neu. The problem, of course, is that it's a very small fraction, but that small fraction, should be treated with HER2-targeted therapy. And similarly, looking down this list of other drugs, AKT, mTOR, ALK inhibitors are in common use. PARP inhibitors are now being approved for the BRCA-positive pancreas cancer. So there's a lot of pancreas cancers that have a targetable mutation, but we still need to develop additional ones. And then this was, I think, the most unusual and surprising thing we found, was that there's a subset of pancreas cancers that have a mutation in one of 3 genes called MLL or MLL2 and 3. These are chromatin binding genes that play a role in unwinding DNA for gene expression. Now, as you can see, when we look at common genes shown over here, CDKN2 was mutant in a vast number of these patients, KRAS about 90%, P53 about 75%, so it was just as we would expect. But we found these fractional mutations. 7% had MLL3, 5% MLL2, 2% MLL. And you'll also notice on this slide, I don't know if I can, that these 3 never occurred in the same subset. That is, having one was sufficient. And if one looked at the survival of those, of those 3 groups, which is shown in the blue line down below, it was much better than the survival of patients who were wild type for one of those 3 genes. So again, we're defining a subset of pancreas cancer patients, probably 15 or 20%, who we could predict are going to do pretty well. And we're also defining a much bigger subset who we predict will do pretty lousy, because all these patients had Whipples, 90% of them got adjuvant therapy, and yet the median survival of the wild type group, who were not mutant for the MLL genes, was on the order of 13 or 14 months. So that subset of patients, we need to do something different, because clearly what we're doing with traditional surgery and adjuvant therapy isn't working. The other thing that came out of this study that was interesting was looking at circulating DNA, and we could find KRAS mutant DNA in the circulation of pancreas cancer patients. And this just shows some small numbers, but interesting data. On the left panel, you can see that there are a group of patients who had Whipple operations, and then we looked for circulating tumor DNA in their serum after their operation. And we broke those into the group that had no tumor DNA detected or the group with DNA detected. You would predict that if you have your cancer removed, there shouldn't be any more tumor DNA, mutant DNA, in your blood. And in fact, what we found was the group that had no circulating tumor DNA had a very good long-term prognosis, 60% long-term survival, whereas the group that had circulating tumor DNA, even though they apparently had margin-negative resections in some cases, negative nodes in some cases, they had a very, very high incidence of recurrence. So again, we're able to begin to make prognostic information and hopefully design trials based on that kind of information. Of those who did recur, it was interesting that on the left-hand panel, you can see that the time of those recurrences based on CT imaging or circulating tumor DNA analysis. And again, the DNA may give us the information much earlier than things like CAT scans. So again, the sort of molecular analysis may allow us to identify high-risk patients, favorable patients, patients who should be treated with different agents, and ultimately may also be useful in sort of post-operative staging and in surveillance for recurrence. So in conclusion, I think there are multiple subtypes of cancer, of pancreas cancer, but the exact molecular definition of these subtypes and their implications for prognosis and treatment are in evolution. We have multiple studies now. We have to begin to put all the data together and decide really what are the different groups. Our study, as well as other studies that have subsequently been published, have shown that there are multiple targetable mutations in patients with pancreas cancer. We ought to be doing this genomic approach for patients and offering them treatment that has at least a theoretical and mechanistic reason to think would inhibit their tumors. Circulating tumor DNA may inform prognosis and treatment, and defining favorable and unfavorable subtypes of pancreas cancer should drive new approaches to clinical trials. Again, it's my great honor to be here, and thank you very much.
Thank you, Nir, for the too kind introduction. It's a great pleasure to be here. I'd like to thank the organizer, Yossi and Moti, for inviting a non-surgeon to speak here. Actually, it's quite exciting to me. Maybe some of you know that I started my medical career at the surgery department at Soroka Medical Center and later at Sheba Medical Center as a soldier in the Yom Kippur War. And then, you know, by identification with the aggressors, I decided to become a physician. But also I realized that for the sake of the patient, I'd better not be a surgeon. And thank you, Jeff, for the amazing introduction. It will be nice, much easier for me to discuss what we have learned from the thousands of genomes, of cancer genomes that were gathered over the last few years. And as you know, and as you just heard, until 2000 or so, we learned about the genetic basis of cancer by amazing work of many laboratories that actually studied gene by gene, protein by protein. Probably the best example is what we learned about colon cancer. This is from the group in Johns Hopkins, the Bert Vogelsen team, that were able to show the stepwise acquisition of somatic mutations that result in cancer in general, with the fantastic example of colon cancer. And then, actually, as early as in '86, Delbecco, the Nobel Prize laureate, suggested, he was one of those that suggested to establish the Human Genome Project, but as early as '86, he also suggested that the best way to advance cancer research is by performing a cancer genome project. And indeed, very soon after the sequencing of the first human genomes as part of the Human Genome Project, came in parallel two cancer genome projects. One headed by the NCI, it's also known as the TCGA project, that sequenced thousands of tumors and compared these sequences to the normal tissue of the same individuals, and also an international consortium that did the same, and actually there is a very nice collaboration between this project. As you just heard and saw, the price of genome sequencing is going down very fast, so now actually you don't need an international project, because the new machine, this is the Illumina new machine that was launched a few months ago, actually will bring the cost of complete human genome to 100,000. Therefore, everybody actually can do it. So it's time now to look back and start to think what we learned from those thousands of genomes that were analyzed. So we know that there are a lot of mutations in cancer. The majority of them are single base substitutions, single nucleotide mutations, but there, in addition, there are translocation, insertions, deletions, insertions, and amplification. We also learned that there is difference in the number of mutations between different tumors. The most impressive difference is between pediatric cancer and the adult solid tumors. The number of mutations in the majority of pediatric cancer is very low, while that of the majority of solid tumors of adults is very high. And this is not surprising because from the first moment of our life, actually at the stage of the fertilized egg, we start accumulating mutations, and it depends on how long you live, how many mutations you are going to acquire. This is true for any cell in our body, but in particular for cancer cells. And here you see the number of mutations in pediatric tumors is very low, very similar. Many of the hematologic malignancies are also characterized by very low number of mutations, and then the majority of solid tumors with much increased number of mutations, then a group with very high number of mutations. This is the group where a strong carcinogen is acting, such as melanoma with UV radiation, lung cancer in smokers. By the way, this is the number of mutations in smokers, in lung cancer in smokers, and this is the number of mutations of lung cancer in non-smokers, and we'll come to it later. And at the end of the spectrum, there are few genetic disorders where, due to defects in DNA repair, there is a very, very high number of mutations. So as I mentioned, we start accumulating mutations since we are a fertilized egg, and then all over life. But it's important to remember that the majority of these mutations has nothing to do with cancer. We just accumulate mutations, and I'll come to it soon, and only a few, and as was suggested in the previous lecture, only few of these mutations has to do with activation of oncogenes, silencing of tumor suppressor genes, etc. So we call those few mutations that really cause cancer, we call them driver mutations, and the rest of the mutations are passenger mutations, which are there but are not important. And the main challenge in cancer genomics is to find who are the few driver mutations and which these are the relevant for therapy, for prognosis, etc. Very recently, there is a very hot topic raised again by Vogelstein and his group, and actually they claim, and actually in a very convincing way, that we knew that environmental factors such as UV and smoking are relevant to cancer. They increase the number of mutations. Also, there are few genetic alterations that predispose to cancer. Yet, the highest contribution to acquisition of mutation in cancer is due to what they called in the beginning bad luck. Any replication, any time a cell is divided among the 3 billion nucleotides that we have in our DNA in each cell, on the average we acquire 3 mutations. And those tumors that arise, those tissues such as the colon, where there are a lot of divisions of the stem cells, those are the tissues that will accumulate a lot of mutation, and therefore the chance for cancer is going to be high. This is from a very recent science paper showing the relevant contribution of the environmental factors, the hereditary factors, and the replication, the bad luck factor to cancer. And you see that the acquisition of mutations during replication is the most important factor. One of the lessons that we learned from the analysis of various types of cancer is that the spectrum of mutation is usually not tumor specific. Of course, there are mutations that are more prevalent in a specific type or subtype, as we heard, but you'll find actually the same mutations in many types of cancer. Therefore, when you think about future therapy of cancer, it's more relevant to know the mutations in the gene than to know the precise way, the name that the pathologist gave to the tumor. And of course, the challenge is to find the best therapy, individualized therapy for every tumor. And luckily, we have now hundreds of new compounds, rationally designed drugs that are directed to a specific protein, specific mutation, etc. This is from a very recent paper, actually went on advanced online in Nature Medicine 2 days ago from Sloan Kettering, where they summarize their experience with prospective study of 10,000 tumors, all metastatic tumors. And the conclusions are very relevant. You see that there are tumors such as GIST, where you'll find driver mutations in the majority of tumors, but the number differs, and there are tumors where you find driver mutation only in the minority of them. These are the type of criteria that allow you to tailor the therapy. So there are drugs that are FDA approved for this particular type of cancer. There are non-FDA approved, etc. I won't go into the details, but altogether they were able to enroll 11% of the patients into clinical trials. So in the future it will go up, but not probably to very high level. Is it working? We know that sometimes we see impressive results, sometimes don't. This is an example from our center. This is a baby that was born with a huge tumor of the tongue that turned out to be a mangiopericytoma. She was operated, but soon after operation, the tumor grew again, and then she was treated by chemotherapy, which did nothing practically. And then we sequenced the genome, and we found a BRAF mutation, similar to the BRAF mutation that we find in melanoma, colon, lung cancer, etc. And she responded amazingly to the BRAF inhibitor. And until now, she's absolutely okay. So this is a good example. However, this is the exception. As you all know, the majority of targeted therapies that are successful are limited in time. When you give BRAF inhibitor to melanoma or EGF inhibitor in lung cancer or colon cancer, within few months, and if the patient is lucky, 2 or 3 years, the tumor will recur. So now we're facing the challenge of how to go ahead with rational therapy and improve the results. Just to remind you, this is a typical tumor, in this case of the pancreas, and there are several studies that the tumor was sampled in different regions of the tumor and sequenced. And there are mutations that you'll find in this part of the tumor and not in this part. Even more so, these are 2 metastases. When you sequence them, there are mutations that are common to both mutations, or both metastases, or to 5 metastases, but there are also metastasis-specific new mutations. Even more so, when you analyze the different regions of the single metastasis, you will find differences. So now when we and many companies should tell the patient, okay, let's biopsy your metastasis and tailor the best therapy for you right now, this is not relevant to the other metastases. So one of the main conclusions that are emerging that probably this is not the best way. Again, from the group of Vogelstein in 2012, they looked at the outcome of patients that were with colon cancer that were treated with EGF receptor inhibitors. And it turned out that this example of 2 patients that responded, however, there was relapse 1 day. And then using what we just heard, the analysis of KRAS mutation in the plasma of the patient, they were able to show that parallel to the relapse, there is emergence of KRAS mutated clones. In this tumor, 4 of them. In this tumor, 2 different KRAS mutations. And mathematical analysis indicates that these clones, in the majority of cases, were present before therapy was initiated, indicating that the failure of targeted therapy by single drug is there at the beginning. So this is another study from a similar group that went ahead and looked for mutations in, again, under anti-EGF receptor inhibitors, looked for mutation in several genes using genomic approach, and you see this waterfall, all these are failures of therapy. These are the responders. You see that in many genes, there are new mutations. Again, many of these mutations were present in a very low representation before therapy was initiated. So how can we proceed? How can we improve the results? So one approach is to combine therapies. Very similar to the situation with AIDS, with therapy to HIV and AIDS. Remember, the first inhibitors that were used as a single drug, using a single drug approach, did very little. However, today with cocktails, this is very successful. So in this study, the combination of various inhibitors to various targets in the tumor improved the results significantly, and probably we are heading into this direction. Another approach, which again was mentioned by Jeff before, is what is now known as liquid biopsies or analysis of DNA, of free DNA in the plasma. And we know today that among tumor cells, there is apoptosis, necrosis, secretion of endozymes, and all the exozymes, and all these result in the emergence of DNA that derived from the tumor in the peripheral blood. And by the analysis of this soluble DNA, we can biopsy all the mutations that are present in all the metastases together. So bad news for surgeons, we won't need you in the near future too much to have another biopsy when new metastases are coming. However, don't worry, it's going to become much more optimistic soon. It's not only blood, you can analyze various types of body fluids looking for mutations in the tumor. In the first stages, people were able to analyze only one or 2 genes, usually KRAS, P53, or both. Later, a specific set of genes were analyzed on peripheral blood, and now there is a way to do all genome sequencing of the tumor by analyzing the peripheral blood, very similar to the sampling of fetus in maternal blood. And this is the way we are going to treat patients in the near future. Actually, we are there already. So you give the first inhibitor, then you follow by soluble DNA. You see the emergence of a second clone. You change the therapy, etc. And as I mentioned, probably in the future you'll use a combination of drugs. So you'll have a patient, you analyze the spectrum of mutation, you start rational therapy, you follow the circulating DNA. If everything is okay, you continue. If there is emergence of new mutations, new clones, you change therapy. However, probably, as we heard, this is very relevant to follow-up of therapy, minimal residual, etc. However, probably the most promising approach is to use the circulating DNA for early detection. And probably, and we are not there yet, the methodologies now allow us to sample advanced tumors, but to detect DNA from a tumor which is very, very small, this is not very successful. However, it's a technical problem which is going to be solved. So hopefully in the near future, when the technology will allow, instead of sending patient to colonoscopy and chest CT, etc., you'll follow the patient by annual or so analysis of circulating DNA. And if you'll find specific mutation, this is the time that surgery is the most important, because in this audience I don't have to tell you that the only way to cure the majority of patients is by surgery. So in the near future we'll be able to detect the very small tumors, take them out, and for the majority of the patients this will cure them. And just to show, this is from a week ago, 2 papers, one in Nature, one in New England Journal, indicating that indeed the follow-up of soluble DNA, or what is called as the liquid biopsy, is turned out to be successful. And so this is one of the main avenues where the analysis of genomes will take us. And in the last 2 minutes, just actually as an introduction to the lecture of Gal Merkel after me, is the role of the immunotherapy. Again, in any therapy that was used until now, conventional chemotherapy, tailored therapy, those tumors that have a lot of mutations usually are those that are difficult to treat. And it's not surprising that the nice example that I showed you with this girl is with a very simple tumor of child where the number of mutation is low. Similarly, in chronic myeloid leukemia, there is the BCR-ABLson, which is the main driver gene. With imatinib, you can cure or treat the majority of patients. This is not true for those tumors, the solid tumors, where there are a lot of mutations. There is only one situation where high number of mutation is good for the patient, and this is when you use the immune system. And without going to details, you are all aware that we use these days the checkpoint inhibitors and similar drugs. And again, remember the example of the number of mutation of lung cancer in smokers and in non-smokers. EGF receptor inhibitors, chemotherapy, anything that was used in the past in lung cancer was much more successful in patients in non-smokers. However, immunotherapy practically is going to work only in smokers because the number of mutation make these tumors different from the rest of the body, enable the immune system to recognize these malignant cells as foreign and attack them, and using checkpoint control and other things that we are going to hear from Gal, we can just improve this approach, but the number of mutations in this case help us to treat the patient. And this is from a New England paper showing that when you treat melanoma with anti-CTLA-4, those patients that have more than 100 mutations have much better prognosis than those that have less than 100 mutations. Similarly, in lung cancer with anti-PD-1, again, those patients with high number of mutations do better than those with low number of mutations. And it's not only the number of mutations. Actually, there is a way these days to predict who are the mutations that will change a specific peptide which will be presented by the HLA of the particular patient. And actually, you can show that there is very nice correlation between the number of mutations that result in presentation of specific peptide and response to therapy. And 2 examples in colon cancer, you are aware that there is one subgroup where there is a mismatch repair defect and very high number of mutations. Those are the colon cancer patients that respond to checkpoint inhibitors. And similarly, in colon cancer, there are 2 subtypes that are predicted to respond very well to immunotherapy. One is the subgroup with mismatch repair with large number of mutations, and the other one is a small subgroup where a specific region of chromosome 9 is amplified, and this is where the PDL1 and the PDL2 antigens are encoded. In these 2 subgroups, anti-checkpoint inhibitors are predicted to be successful. And I leave the rest of the immunotherapy to Gal. Thank you.
Avi, thank you. Really, I think that you, like Didi said, you were too kind, really too kind. And I would like also to thank Professor Yossi Klausner for inviting me here and to speak here in front of you today. I must share with you that to come up here and speak after two really not only super eloquent speakers but also really prominent people such as Jeff and Gidi is challenging. So I'll try my best. So let's see how this works. So I'm going to talk about some thoughts about how immunotherapy sets a new course in oncology. And I can enjoy the extensive background that both Jeff and Gidi already told you, so it is going to be very helpful for me. So in order to try and understand how we can treat cancer, we need to understand what drives cancer. And we already heard from Jeff, I think, in Jeff's talk about the hallmarks of cancer, which is a set of 10 different features that a normal cell needs to acquire in order to be a clinically evident disease, and not just cell lines that run in the lab. And these features include cell proliferation, avoiding death, to induce blood vessels, etc., etc. And the idea here is that each one of these hallmarks provides the basis to undermine any one of these hallmarks in order to treat a patient. The bread and butter in oncology is still, in many cases, chemotherapy and radiotherapy, and these are non-specific modalities which are limited by non-specificity and the toxicity, and this has led to just incremental advancement over the last decades. So we've heard a lot now about genetics, cancer genomics, and the ability to identify various cancer-specific dominant metabolic and molecular pathways within the cancer cells, which could lead, or not could, which already led to the development of various targeted therapies, such as BRAF inhibitors, ALK inhibitors, EGFR inhibitors, so on and so forth, which we routinely use in the clinic. And these are efficacious drugs, usually quite tolerable, but we must understand, and Gidi showed it very, very nicely, that the cancer genome it doesn't look like that as we thought 17 years ago. It probably looks something more like this. So now to try, it is definitely helpful in order to try and drive some molecular subtyping, and we heard from Jeff about the differences about you can classify the same group of pancreatic cancer patients, but if you use different classifiers, you can reach maybe different conclusions. We still need to understand better how to integrate all of that into clinical practice. Not to mention that it is very optimistic to think that if we do something here, it will cure cancer. And we know that targeted therapy provides great benefit, but it still hardly ever cures patients. So this clearly calls for a paradigm shift. And we all have the immune system, and the immune system is characterized by a huge heterogeneity. We have billions of different of clones. The system is adaptive. It can learn. It can chase the ever-changing cancer cell, and it also has the ability to induce memory. So the immune system has, let's see if it works, the immune system has a wonderful capacity to eradicate cancer cells. So if you take a look at over here, the large cells are cancer cells, the small cells are lymphocytes from the same patient, and the lymphocytes can very nicely eliminate cancer cells. But we know that already for more than a century. And various attempts to wield the power of the immune system to treat cancer, we've been trying to do that for more than a century, usually by stimulating the immune system with interleukins, interferons, vaccination strategies, so on and so forth, and that has led to a century of frustration, clinical frustration, scientific frustration. Nevertheless, I'm standing here, something clearly changed. Human biology hasn't changed over the last 100 years. The thing that changed is our understanding of what's going on. And with the pioneering of surgeon, Steve Rosenberg, who is one of the founding fathers of immunotherapy, who laid the foundations for ideas, and he also did series of seminal work to drive the understanding of this field forward, all the way to our current era, something has changed. And the thing that has changed is this understanding. Cancer is not an infection. Well, it's not just something semantic. And if you come to think about it, we tried to treat cancer as if it was an infection from the immunological perspective. We've been trying to boost the immune system because we know that if the immune system is weak, we are more susceptible to infection. So we thought, okay, if the immune system is weak, we get cancer, we need to boost the immune system, and that has been failing. Well, cancer is not an infection. Cancer is something that arises from within. It takes many years for the developing cancer cells to co-evolve together with the immune system, and only when the cancer cells become fully resistant and escape the immune system, only then we see the patient. So it means that the tumor outsmarts the immune system. It's not a weakness of the immune system. It's the tumor that outsmarts the immune system. When we see the patient for the first time, the immune system is already lost, not because it's weak. It's something completely different, and we need, in order to wield the immune system, we need to neutralize tumor escape mechanisms. We need to reprogram the immune system. When I say to neutralize tumor escape mechanism, what do I mean? This is just a nice example that I always like to use. If these are cancer cells, for example, so if the cancer cells make themselves disappear from the immune system, and you want to treat this condition, the fact that you don't see them, it doesn't mean that they are not there. So if we are now going to provide new, bigger guns for the immune system, it just won't work. What we need to do is to deactivate this mechanism and make the cells visible again to the immune system. And at the moment, the star of the show of these types of mechanism is called the PD-1 or PD-1 axis. PD-1 is a molecule. It's a physiological molecule which is expressed by the immune system, by the cells of the immune system, and its purpose is to control the immune system, to shut down eventually the immune response. Every good thing must come to an end, right? So this is the purpose of the PD-1. The problem is that cancers, they take advantage of this physiological mechanism, and they shut down the function of the immune system prematurely. So if we would be able to break down or to abrogate this type of interaction, we would be able to treat cancer. And we also identified something which functions similar to PD-1, Avi mentioned that. And I would like to show you here with video microscopy technology, how does it work? So we labeled melanoma cells from a patient with red, and we incubated them together with lymphocytes from the same patient, and either with no agent or with the agent that we developed. And the beauty of this system is that when the melanoma cells start to die, they change their color from red to green, so it's very visible. Now let's see if it works. Let's start first with the left part. Okay, so it's going to be simultaneously. So you can see and compare what's happening between the left. It does. Okay, so this is the difference. I'm sorry about the technical stuff, but usually it's supposed, the first thing is supposed to run, then the second, but nevertheless the difference here is huge. All of these are dead melanoma cells. You can start seeing, we can see how it works here. I'll switch to video. אתה יכול להפעיל את השמאלי קודם? But anyway, the nice thing about it is usually when we read papers, when we read publications, we see all of these graphs. Today, with technology, we can actually see what's going on in real time. And we can see how the immune system attacks, how the cells, they bash into the cancer cells. They cluster them together. They encircle them and start killing them. So, and the difference here is huge. The antibody itself, it doesn't kill the cancer cells. It just releases the brakes of the immune system. I'll move because it just wasn't, it didn't work as successfully as I hoped for, but I hope that you got the idea. Now, these types of agents, PD-1 axis blockade, has completely altered the way that we treat melanoma. It caused a dramatic paradigm shift, significantly prolonging the survival of melanoma patients when treated in the first line or advanced line. And that's not just in melanoma, it's also in non-small cell lung cancer, and also in RCC, Hodgkin's, recurrent head and neck, urothelial cancer, all of these are FDA-approved indications, 6 different indications in just 2 years. So this is really remarkable, but it is still far from where we want to be. We must get it better. We still have more than 50%, 60% of the patients with primary resistance, and a substantial proportion of the patients with secondary resistance, and I'm not talking about cost. This is something completely different. So how can we move forward from what we know now into the future? We need first to understand how the immune system recognizes cancer. It's very easy to understand how the immune system recognizes pathogens, different DNA, different proteins, antigens, foreign. They're recognized as foreign, very, very simple. What about cancer cells? They are derived from our own cells, allegedly the same genome. So we heard about the driver and passenger mutations. So out of the thousands of different mutations that are accumulated during cancer development, some of them do cause some immunologically important alterations in the DNA, different proteins, which marks foreignicity of or danger of the cancer cells. These are called neoepitopes, and if you come to think about it, the more mutations, you heard about it from Gidi, the more mutations, it's like the lottery. The more mutations there are, the higher the likelihood that something of immunological significance would occur. And these are the passenger mutations. So these are discrete mutations. They are unique to each patient. It's not like KRAS, which is in 40% of the patients. Each passenger mutation is unique to the patient, no biological advantage, and therefore these mutations are useless for tumor classification. You can't take these genomic data of passenger mutations to classify tumors. What can we use? How can we use this data? We can talk about mutational load, this lottery concept. And indeed, we can classify the tumor histologies into different categories. These are high mutational burden, medium, and low. And among the high mutational load, we can see the melanoma, the smokers, urothelial, and MSI high. And all of these are FDA approved. This is going to be approved within less than a month with wonderful data. I'm talking now about the PD-1 axis blockade. What about this type of tumors? Just medium amount of mutations, but we have lymphoma, RCC, head and neck, and these show similar efficacy to what we see here. So, there is a huge difference in the amount of the mutation. So clearly there is other factors playing a role here. And what about the last group over here of breast, prostate, pancreas? Do you really think that the immune system has no role here? That they are not immunogenic? I seriously doubt it. The immune system has a role and interacts with all types of cancer. We still need to understand what's going on here. And for that purpose, we need first to understand how the immune system recognizes cancer. So it's a 3-stage process. Immunological information is picked up, it then processed, it's presented to the immune system in the lymph nodes to pick up the right cells, to activate them, stimulate them, expand them, and these cells circulate throughout the body and try to eradicate the cancer cells. So now we need to understand how tumors deal with the immune system. So this is the framework of the immune system. Now let's try and categorize what's going on. So in some cases, the immune response is elicited, and all of the right cells, they are generated, they infiltrate the tumors, and we have T cells with a lot of tumor-infiltrating lymphocytes. So these are T-cell inflamed tumors. In all of these cases, the tumors, they are devoid of T cells. So what's going on here? So maybe there is a problem in the recruitment of the T cells into the tumor. Maybe there is a problem in the priming. Maybe there is even a problem in the initiation of the immune response. So and clearly the tumors play a dramatic role in all of these aspects. So if the tumors are infiltrated by T cells, clearly the tumor deals with this type of inflammation, and it does so by actively suppressing locally the immune response, by using suppressive cytokines, suppressive microenvironment, PD-1, etc. But it plays a role only in this part. Over here, This is called immune exclusion. The tumors can exclude the effector cells, and tumors can even abrogate the ability of the immune system to elicit an immune response. This is called immune desert. And today we know about a lot of mechanisms. This is just some sort of representation. We can depict, we can describe these machineries or these mechanisms by molecularly or biochemically. So what can we do about it? If we want to help the effectors, this is one strategy to augment the ability of the T cells either to go into the tumor or to overcome the local suppression. Another thing that we can do, we can increase or improve the training of the immune system, or we can perhaps enhance the intelligence, the picking up of the immunological information. So we know how to help the effectors with PD-1, and there are other strategies. There are also new strategies to increase or overcome the immune exclusion. I'm not going to go into that because this is something that I don't have the time to talk about. But also we can improve intelligence. What is immunological intelligence? It's immunological information. So in many cases, at least in oncology, they say, okay, give chemotherapy, give radiotherapy, kill the cancer cells, spill the antigens, and then it would boost the immune system. Well, this is way too simplistic because the cells, the antigens must be spilled in a way that the immune system can interpret them. I mean, you can bring me all of the information in the world. If it would be written in Chinese, it wouldn't help me, right? So the cells must be killed in a way that would be interpretable for the immune system. And by the way, cells in the body, they die all the time. And they don't stimulate the immune system. But nevertheless, if a single cell is infected with the virus, it boosts up the immune system immediately. So this is something that we need to copy. We need to understand how to kill the cancer cells in a way that would be relevant for the immune system. And this is not something entirely trivial. So today we are talking about devising a new language. We are used to speak in oncology in terms like in anatomical terms, like breasts, like body parts, in histological terms, adenocarcinoma, squamous carcinoma, etc. And now we are also speaking in terms of genomic terms, various types of molecules and mutated genes. All of these are very relevant when we are talking about strategies that target the tumor. If we are talking about modulating the immune system, this is modulation of the host. Personally, I'm not convinced that the immune system really cares whether a cancer cell comes from one body part or the other body part. Just exactly such as a neutrophil doesn't really care whether a certain bacterium is of one type or the other type. It's the biological interactions, the mechanisms between them that are important. And such thinking is going to transform the way that we look at cancer indications. MSI high, this is the first example. MSI high could be of GI origin, endometrium, whatever. The histology isn't really important. If a tumor has very, very high load of mutations, it's going to respond to PD-1 blockade. The FDA is probably going to approve that in a month or two. So we need to add a new layer of how we classify and treat cancer. We need to add on anatomy, histology, genomics. We need also to create some sort of an immunomap which describes, this is a framework to describe the way that in the immune system and the cancer cells interact according to mechanism. And this is going to create new classifications of tumor. We are going to be able to personalize the immunological interventions that we are going to administer to the patients. This is, for example, a tumor that would respond to one strategy. This is a sequence, another strategy. All of that independently of the histology. And this is going to help us also to choose the next lines of therapy. We heard about it from Gidi with the example of liquid biopsies. So this is probably going to help us also in immunology. And this is now the last slide. How are we going to integrate genomics, proteomics, functional data, clinical data? It's crazy. It's just crazy amounts of data retrospectively, prospectively. So we need here the help of computers, big data, algorithms, machine learning algorithms, AI and deep learning. These are now the buzzwords, but this is not going to be the future. It's already the present. It's going to manifest into clinical practice, I believe, very, very, very soon. So with that, I'd like to conclude, and thank you for your attention.